Okay, so I think we're live. Hello, 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 hello. Hello, stream. Hope everyone's doing well. Welcome, welcome. I guess I did want to say a word before we started today. One of my coworkers, his mom is sick in the hospital, and I just hope the best for her and for him. And kind of sat here thinking for a moment, like, man, I'm not very close to my coworkers, and I don't know. I guess all I could say is I hope the best for her and for him. And that's what I don't know. I don't really. It's one of those things you're confronted with that. It's like I don't really know what to say or to do. I don't really. So let me do this. Well, so I hope the best for her, and I hope she gets better. So, okay, so what today's video is going to be about or today's stream is, I was looking at a problem yesterday that was involving Eulerian paths, an Eulerian path, and I conceded that I wasn't able to solve it without an algorithm that I didn't know. So let's go ahead and take a look at that algorithm and write an instance. I'm just going to set a timer so I know when to stop today. Try to get a few hours in here of sort of studying and programming. And excuse me. So yeah, Eulerian paths. So we'll look at that algorithm, learn it, and program it. Be a little sad that we kind of took this problem for granted. Had a humbling experience. Excuse me for yawning. I've been staying up too late. So yeah, let's do that. That'll be the plan. So part two, here we go. Reconstruct itinerary. Given a list of airline tickets represented by pairs of departure and arrival airports from and to, reconstruct the itinerary in order. All of the tickets belong to a man who departs from JFK. Thus, the itinerary must begin with JFK. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order when read as a single string. For example, the itinerary JFK to LGA has a smaller lexical order than JFK LGB. All airports are represented by 3 capital letters, IATA code. You may assume all tickets form at least one valid itinerary. One must use all the tickets once and only once. So we have an example, MUC, LHR, then from LHR to SFO, then SFO to SJC, and then, JFK to MUC, that's the first one. JFK to MUC, then MUC to LHR, then LHR to SFO, and then SFO to SJC. And you put that all together in the bottom here. And the next example, they give you a few other tickets, and they give you an output, right, put together from the tickets. And you notice also that there are actually 2 possible paths you could have taken, 2 constructions. And the one that's in the smaller lexical order is the one that they're after, they're requesting. So my first approach to this was to just kind of follow the tickets. And then I thought, well, actually, if you need the right lexical order and then you have multiple options, why not basically sort your options for each airport, right? So one airport, you have multiple tickets from that airport, so you have sort of, it's almost like a graph, where you have multiple edges. However, as it turns out, if you do it that way, and you just basically prioritize the airports that have the alphabetically smallest names, then you can run into a situation where you jumped from one airport that has multiple choices to another airport, or maybe there's no choice from that airport out. So you can't actually have a full path that uses all of the tickets. And so if you take this idea a little bit further, that maybe this is like a directed graph from and to, a digraph, and each ticket is like an edge from one airport to another, where the airports are the sort of the vertices in the graph. This kind of lends itself to that approach, that analogy. The problem you run into is that you cannot just do as I described. That algorithm doesn't work. It won't be correct, rather. And so, okay, what do we do? Well, as it turns out, a graph, a tour or a path that uses every edge in a graph, or digraph, or undirected graph. One of the undirected graph means that it's not a from and to. There's sort of, you can go both ways. There's just a connection. The path. A path through the graph that uses every edge is called an Eulerian path. And so we have the wiki article. And I kind of skipped ahead a little bit to Helmholtzer's algorithm, which is a more efficient way to find Euler cycles. And this is more efficient than Fleury's algorithm, which is another algorithm to find these cycles. Well, you can call them cycles. Paths are the same, similar thing. Cycle basically means that you end up, back at the starting either vertex or edge. I want to say start the beginning vertex. A path, obviously, you don't need to start at you don't need to come back to the vertex. So. Excuse me. So, there's one more concept here before we get into that algorithm. One more concept I wanted to briefly talk about, which is this arborescence. I was trying to think about. They said every arborescence is a directed acyclic graph, but not every DAG is an arborescence. And I wasn't totally certain about that. I didn't really understand. And I think the reason is that if you had, so I'll explain those things in a moment. So if you had something like this, so an arborescence is kind of like, it's basically like a tree, but it's a graph, a directed acyclic graph. It's like a tree and a digraph, a rooted tree and a digraph. And it's actually, it's actually, the reason it's an arborescence is because it's not necessarily a binary tree. It's just like a tree. It's a subgraph, I believe, and it's a subgraph of a digraph, directed graph, right? Exactly, one directed graph from U to V. Right, now what's important about this though is what's important about this is there's only one path to each node. Now what can happen is a directed acyclic graph, by the way, is very similar, but the difference between an acyclic graph and an arborescence is that there could be more than one path from the root to one of the nodes. DAG is very similar. However, you notice that even though you've added this what do they call that? Even though you've added this edge, it's still not cyclical. This doesn't create a cycle, but it does create two paths to that node. Whoops. So that's the difference between an arborescence and a DAG. is basically DAGs would allow edges like this, which is kind of a subtle thing, but that's the reason why. Because I thought about it, I was like, wait, why is that? What do you mean? What do you mean every DAG's not an arborescence? That's why. It's usually a subgraph. It doesn't actually have to be a subgraph. It could be as I think the definition they give that there's only one path from the root to that node is a good one. I think that's sufficient. Excuse me. Excuse me. So, Helmholtzer's algorithm. All right, let's learn. So there was this idea I had briefly where I thought, well, maybe I could try to think up my own algorithm for this. I thought, nah, we have too many other things that we want to do right now. I want to just read an algorithm that could work, implement it, and then go to the next question. Quite frankly, I don't want to go too deep into this. Try to come up with my own. I do often do that when I'm looking at these problems, the questions. If I don't know of a way to solve them, I try to come up with something on my own. I think that's like stretching your mind. It's healthy in some regard. It's kind of like exercise. However, it's not always great. It takes a lot of time, and it's also like something that has someone's name after them. Usually, it's like can be pretty difficult to think up on your own. So I try not to do that too much. Although, yeah, I mean, there's this tricky thing when you're dealing with like arbitrary maths problems and computer science problems where there's often a lot of theory involved with other like tools and other ideas that other people have come up with over the years. And if you're not familiar with those things, it can be really challenging. So like a good example would be there was a problem we worked on that makes use of the SG theorem from game theory in order to find an efficient solution. And it's extremely efficient, the solution. However, the problem you run into is you need to know what that is. You need to be aware of that, right? You need to learn to kind of know that in the first place. And obviously coming up with that on your own is like, it's a little bit much, it's like a bit much. So anyway, so Helmholtzer's algorithm. All right, Helmholtzer's 1873 paper provides a different method for finding Euler cycles and is more efficient than Fleury's algorithm. Choose any starting vertex V and follow a trail of edges from that vertex until returning to V. It is not possible to get stuck at any vertex other than V because the even degree of all vertices ensures that when the trail enters another vertex W, there must be an unused edge leaving W. The tour formed in this way is a closed tour, but may not cover all the vertices and edges of the initial graph. As long as there exists a vertex U that belongs to the current tour, but that has as long as there exists a vertex U that belongs to the current tour, but that has adjacent edges not part of the tour, start another trail from U. As adjacent edges not part of the tour, start another trail from U, following unused edges until returning to U, and join the tour formed in this way to the previous tour. Since we assume the original graph is connected, repeating the previous step will exhaust all edges of the graph. By using a data structure such as a doubly linked list to maintain the set of unused edges incident to each vertex, to maintain the list of vertices on the current tour that have unused edges, and to maintain the tour itself, the individual operations of the algorithm, finding unused edges exiting each vertex, finding a new starting vertex for a tour, and connecting two tours that share a vertex, may be performed in constant time each, so the overall algorithm takes linear time. Okay, I really gotta think about this. I think it's possible that my own algorithm, I don't know, I'm not sure, actually, I'm not sure. I want to say something like the algorithm that I chose, which was the depth first search algorithm. Possibly if I had instead used something along like this, something more like this, a smarter data structure, or smarter implementation of the data structure, then it would have been more efficient, something like that. I'm not really sure though. Something about that doesn't seem totally correct. This algorithm may also be implemented with a queue because it is only possible to get stuck when the queue represents a closed tour. One should rotate the queue, remove an element from the head, and add it to the tail until unstuck, and continue until all edges are accounted for. This also takes linear time, as the number of rotations performed is never larger than E. Oh, interesting. Okay. So we're looking for trails, though, not necessarily circuits. I mean, in theory, it's the same thing. Now the thing that's tricky about this is, well, there's a few things to consider now, actually. So I guess the first thing is, the degree of all vertices ensures that when the trail enters another vertex W, there must be an unused edge leaving W. Yeah. There's only one, like any. Interesting. If there's a tour, excuse me, yeah, if there's not a cycle but a tour, that means that there's got to be one vertex that has one more incoming edge than the number of outgoing edges, and that's got to be the last node that you jump to. You can kind of create your tour going backwards from there, can't you? Maybe, I don't know. I'm actually not sure now. I wonder if there is maybe a better way that I can do this algorithm. Because, I don't know, I'm not really sure. I mean, cycles and tours, they're not quite the same thing. They are similar. Okay, here we go. This is what we want to know. A directed graph has an Eulerian trail if and only if at most one vertex has out degree minus in degree equals 1. At most one vertex has in degree minus out degree equals 1. Every other vertex has equal in degree and out degree, and all of its vertices with non-zero degree belong to a single connected component of the underlying undirected graph. Interesting. Yeah, that's what we've got. So there's going to be one vertex at most. One vertex is going to have the in degree minus the out degree is 1. And another vertex could have. Now if this is kind of confusing because if both of these are 0, in other words there's no vertices, it's kind of misleading how they explain things on Wikipedia sometimes. If there's no vertices that have a difference in degree and out degree, that all the vertices have equal in degree and out degree, then it's not an Eulerian trail, it's an Eulerian cycle. Excuse me. You can't have an Eulerian trail at that point. You really need to have either or. Either, I think it's, I'm actually not sure. Can you? Just thinking if it's 2, 2, and 2, right? This gives you your cycle. If you want a trail, you can't connect these, right? You gotta have this one, 1, 2, and then this one is 1, and this one has 1. I want to say you have exactly 1. I mean, is it possible to have? No, as soon as you reach this node, no. Can you do this? Well, it's at most 1. I think it's got to be exactly 1. There's got to be basically a starting point and an ending point. The problem with picking like an arbitrary starting point is that this has no entry, and this has 1 less exit than has entry points. I don't know how you can, like this, it says at most 1, right? I want to say that it doesn't really make a lot of sense to me because I think it needs to be exactly 1. Let's find more information about this. Let's go to Wolfram Alpha. They're usually pretty good. Eulerian path, also called an Euler chain, Euler trail, Euler walk. Walk, choose each graph edge exactly once. If and only if it has at most 2 graph vertices of odd degree. We want a digraph. That doesn't really help us too much. I think we would need like a textbook on this or something like that. Like we need to go to find a resource on Eulerian paths. I don't know. Can we go to this? Can we look at this? Something on math courses. I don't know. Eulerian trail. Is this better? Math world. Isn't this the same thing or a similar thing? No. Courses. One more than just Wikipedia. Like there's got to be something. They're in graphs. Excuse me. No, not really what we're looking for. Constant amortized enumeration of Eulerian trails. Whoa! This was a month ago. Are you kidding? Wow. Two Eulerian trails are edge distinct if the edge sequences are not identical, and they are vertex distinct if the vertex sequences are not identical. As the main result, we propose optimal enumeration algorithms for both problems. That is, these algorithms run in linear total time where n is the number of solutions. Algorithms are based on the reverse search technique introduced by Avis and Fukuda and the push-out auto-amortization technique introduced by Uno. Huh. Huh. Neat. Hmm. Huh. I don't know. I have no idea. Tokyo. Aichi. Japanese. Interesting. Hmm. Hmm. Now, how many trails could there be is the question, right? I don't know if constant's the right word, but anyway. Linear is probably the right word, but anyway. Eulerian circuits, Mantel's theorem, decrees, sequence. Circuit is a closed trail in which the first edge is not specified but the cyclic order is kept. Eulerian circuits. A circuit is a closed trail in which the first edge is not specified but the cyclic order is kept. A circuit is a closed trail in which the first edge is not specified but the cyclic order is kept. A circuit in which the first edge is not specified but the cyclic order is kept. Oh, I see. Okay, gotcha. You don't need to have a first edge in a circuit because it's basically a cycle, right? An Eulerian circuit in a graph contains all the edges. Eulerian circuits. Excuse me, so I'm not looking for I want the trails, right? G has a Eulerian UV trail if and only if the graph G prime obtained by adding to G an extra edge E which ends U, and V has an Eulerian circuit. Right, fair enough. Right. 1.6 for G prime implies our corollary for G. Okay. Yeah, I don't like what they have here. It's just a little confusing. Right, that's way better. Yeah, okay, right. So the difference between an Eulerian trail and an Eulerian circuit is you have G and G prime, where G has an Eulerian trail if and only if you can basically add an edge from U to V, where let's say U is the beginning of the trail and V is the end of the trail. You can add that edge to give you a G prime. If G prime with that edge has that creates an Eulerian cycle, then G has an Eulerian trail. So and G has an Eulerian cycle if and only if every vertex has equal in and out degree, and they're all part of a singly strongly connected component, right? So that means I believe that means that there's got to be, basically you take one of those edges and delete it from the cycle. It's pretty much what you do to go from G prime to G, where G prime, if they all have even in and out edges, if you delete one of the directed edges, that means that one node is lost its out edge and one node lost its in edge. And so there's one node with a difference of 1 of in and out degrees, and then another node of the reverse is 1, right? The out minus in is 1. Yeah, I think it's got to be exactly 1. I think this is worded incorrectly. That's why I was so like, wait a minute, doesn't seem quite right. So can we find, right, Eulerian circuit has an Eulerian UV trail if and only if a degree of every vertex is even degrees of U and V are odd and at most 1 non-trivial. A degree of every vertex is even, degrees of U and V are odd. Oh, this is also for undirected graphs. That's, yeah. See, that's the thing. Like, maybe I'm wrong about this. Yeah, maybe I'm wrong. I'm sorry. Maybe I am wrong. See, that's the thing, is like I have to, because usually it's usually not worded incorrectly, the Wikipedia articles. They're usually like reasonably well worded, I guess, something like that. Like, it's not. So, oh, my freaking back, man. Ugh. It's really annoying. So, I think I could be wrong about this. I think what we just read only applies to, yeah, I was going to say, I need to find an undirected graph. Some of that's still true, that, however, the in and out degrees. I wish there was a reference for this, like an explanation. Let's do Euler paths on digraphs. Let's try that. Digraphs and Euler circuits, in and out degree. Random walk until we form a cycle. Nice. Also, yeah, so digraphs could also be multigraphs. Right, so this is a digraph multi-graph where you actually have what do you call that? You have basically the same edge copied more than once. Right, you can see. Why is this not? Doesn't give me very much, huh? Oops. Didn't mean to do that. Eulerian digraphs, yeah, that's what we're looking for. What? Okay. Looking for just like a really simple. Euclidean cycle. Eulerian. But, okay. No, man, I'm looking for the proof. Okay, one necessary condition, if and only if it has same in degree, out degree. Why the state of being connected is necessary. They actually cover this in the Wikipedia. It doesn't. It's connected components, but not things that are non-zero degree. Right? Obviously, if things are of 0 degree, then you're trying to visit every edge. So obviously, things at 0 degree don't have any edges that are incident. So I'm looking for. So these aren't the questions that I have. The question I have is, how do I verify this condition? I want to say something like, excuse me, I had something on my lips. I want to say something like, if you excuse me, I gotta think. At most is so misleading. Because it suggests that you could have 0. You could have none. Which I don't think is true, right? If either of these are 0, then you won't be able to your cycle won't be able to include all of the edges, because you'll reach every node, right? If it's all, yeah, it can't be at most, right? Because if both of these are 0, then you end up with an Eulerian cycle rather than an Eulerian trail. Right, it's if and only if. If you have both of them, right? If you have both of those vertices, that works. If you only have one of these vertices, I don't know if it's even possible to have. I don't know if it's possible to have a trail. I don't know if it's possible. Yeah, I don't know if it's possible to have a trail when only one of these has. Actually, I guess what I want to say is I don't know if it's possible at all to have this condition where only one of these. Yeah, it's not. No, it's not. So every incident edge contributes. Yeah, you can prove it, right? Every incident edge, every edge between two nodes, it adds one outgoing edge and one incoming edge, right? Right. Some other vertex gets an inbound, and this vertex, it's U to V, right? V gets an incident, it gets one inbound, and U gets one outbound. So every time you add an edge, you increase that amount of the total in degree and the total out degree of the whole graph. In order for there to be exactly one node vertex that has as one of these, right? So sort of you have four options, right? You have, with this at most language, you have four options. You have either 0, 1 for both of those, right? So you have 0, 0, 0, 1, 1, 0, or 1, 1. Either two of the both vertices exist, one of these vertices exists, or they both don't exist, right? They both have even degree. If they all have even degree, you don't have a trail because you have a cycle. If only one of them exists, that means that the total sum, the in degree and the out degree, both in degree and out degree, have to be equal to each other, because every edge contributes one out degree and one in degree. So the total in and out degree has to be the same for the whole graph. If you have all of your nodes have an even number, or have an equal amount of in degree and out degree, except for one vertex, that would give you equal in degree and out degree for the whole graph, except for that one node, that one vertex, which would actually just contradict what we just said, that everything has to be even. Everything has to be even. It has to be the sum of the inbound and the outbound degrees need to be equal for the whole graph, because every edge gives you both one inbound and one outbound, no matter what you do. So it's impossible it's actually impossible to even have a situation where you only have one or the other vertices. So that means that you've got to have exactly one of both. Yeah, that's what I was saying. Okay, I was right. All right, because I'm looking at this, and I'm like, this wording is not correct. This wording is not correct. Like, I'm looking at it like, this doesn't make sense. No, it suggests, yeah, it's not even possible if you have these. So of the four cases, right, which is both, neither vertices exist, so both vertices are even in degree and out degree. Only one of these vertices exists, so one of them has this difference between in degree and out degree, but the other one doesn't, is even, or is equal. Not even, is equal. Sorry, I'm mixing up my words. And then the last case is that both of these vertices exist, just as they are. And the two middle cases you can't even have that in a graph, because every edge will give you an odd and an outbound and an inbound degree, and so the sum of the inbound and outbound degrees for the whole graph need to be equal for all graphs, all directed graphs. Which means that if you had only one of these vertices, then they wouldn't be equal, right? It'd be a difference of 1. So between the total sums, which is impossible as described. It's a contradiction. So then, and the first one we said we end up with it's an if and only if, so we end up with an Eulerian cycle, not a trail. And then the last case is the case that I said, that you need to have exactly one, not at most one, but exactly one. So interesting that they word it this way, but it's wrong to word it this way. It's actually exactly one of these degrees need to exist. Okay. Forgive me for kind of going through all that, but I was like, this is not worded correctly. So basically, we could pretty much assume that every node. No, so pretty much what we can do to find our cycle is we could identify these two nodes that have this difference in degree and out degree, and then draw a connection between those two. Make the graph that has the Eulerian cycle, and then we can apply these algorithms to find the cycle And then obviously just remove that edge at the end. And that would be one approach. That would be one approach. I guess, actually now, if we do it that way, then what I was suggesting earlier about, actually I think the algorithm I wrote could work then. It was linear time. Basically, oh no, it wasn't linear time. It was logarithm. It was n log n. It was some logarithmic. It had a logarithmic extra piece to it, or a logarithmic multiplier, because we're sorting by alphabetical order. So yeah, kind of interesting. I want to say, huh. Yeah, so basically, what you would do, as I said, is you would, how come you get stuck? Wait, why does my algorithm not work in the first place, this original one? The one that was before. Let me go back. Hold on, okay. This is kind of neat. So actually, let me do this. Now you got me thinking. Now you got me thinking, and oh, why my voice is so loud now? Why was it was so low before? Because I wasn't really talking too loud before. Yeah, now I'm like, before I was like yelling into the microphone, I guess. I don't know, when I get excited about stuff, I kind of talk a lot louder. So, yeah, let me turn it down some. Yeah, I'm sorry. I'm looking at I'm looking at my volume, and it was really high. So I'm sorry about that. All of that was causing probably like distortion, I guess. So let me just save this. Let me see something here. Just give me one moment. Okay. I think that's what I want to do. So yeah, something like this. All right, there we go. And actually, I want to. Place, oh, no. Okay. So this TLEs, I think. Yeah, I feel kind of silly now because I didn't really think about this too much. But actually what I had before. Okay, wait. All right, I had something here, and there were some test cases that we had, which we need more of these test cases. Excuse me. So let me explain. Let me explain here. Wrong answer. Nice. Nice. That's good. What's the first one? I think is the right answer. Yeah, second one though. Yeah, so let's go here. So here, go a little further back. There's a little more to do here. I don't know. We want to go basically right before we delete it and start over. Okay. Wrong. All right. Okay. Wait a minute, what? Oh no. No, we had something that was pretty good before. Oh, this is fine. This is correct. Yeah. Okay. Okay. So here's the deal. Here's the problem. What I want to do is, the reason we had an issue with this is that in some cases what would happen is while we're making our rounds here, we would end up in a situation where you couldn't actually finish the cycle, right? And I thought, okay, well then we've got to try all these different paths in order to get this to work properly, which doesn't make any sense. So there's like a few things. So there's only really one problem right here, where there's one node that has, right, there's these two vertices that we would want to find that have this difference in degree, even an odd degree, and you really just want to actually add that ticket to the set of tickets. That's pretty much what you want to do. Now, and that'll give you your cycle, your circuit, and then you basically, once you have your circuit, then you just rotate the solution to the right spot. But it's not just rotating to the right spot. It's, yeah, you can use this multi-set to give you the, what do you call that? To basically keep everything in the right order. Remove edges as you go, pretty much. The thing is, and you could start at JFK too. That works too. That's fine. No, really, it's, no, you know what? No, it's not quite right, because no. It's a little tricky because you don't want to include that edge. You actually don't want to touch that edge that connects. Let's give you the cycle. What you could do is actually start at the sort of the starting edge. Actually, if you start at JFK, it does have to always be sort of the one. Basically, what could happen is you have more than one edge out of JFK, therefore you have at least one edge coming into JFK, and you could sort of take JFK all the way to the ending state, the node that you're supposed to finish at, and the problem you'll have is you get stuck there and you don't actually traverse the rest of the graph, which is what happened, right? Kind of just need to make sure. It's almost like, actually, this algorithm would work if you just take all of the, you can kind of like take all of the edges incident on, so you can find the end point and then kind of trace back the edges for that ending point and say, okay, these edges all have to come at the end, basically in this order. And then you can use this algorithm for the rest of the graph. Basically remove all those edges, more or less. If that makes sense. Just thinking, how would you, I don't know, man, like what is, there was some test case that we had that gave us the wrong answer. It was like, we gotta think about it, we gotta come up with something. I want to say that there's a nifty way to do this that I'm kind of missing at the moment. It's like a way to do this. So if you have something like this, and this goes back, right? So the problem is that you could take this path and you miss these two edges, right? These guys. Or you could take this path and you get all the edges, all of the edges. And what I'm thinking is, right, and what happens is that if you prioritize the sort of lexicographically smaller elements, smaller edges, or really the vertices, the names of the vertices, then you'll end up taking this red one, right? You'll go 0 to 1 to 2 to 3 rather than 0 to, oh no, actually, really if you rename these to something else, like 3 2 1 0, something like this, then you would go 3 2 1 0, right? Instead of 3 2 1 back to 3 back to 1 back to 0. And you wouldn't be able to get out of this 0, right? You would get stuck here, right? You would have, this is a pretty interesting question then. This is like kind of a neat question. You would have, if you added this edge, it doesn't really solve your problem. because even though you removed all you've removed all these edges now as you went, you would reach all of the edges, but now you have this problem where you still need to remove this edge from your list, which just doesn't really work for you. Really interesting question. I like this question a lot. It's a good one. What you'd want to do is, what I was thinking was that if you remove this edge at the end, and now this basically becomes the ending point, and you would, now what happens if you do it this way, right? So this has one outbound edge. The thing is, like, you could have something else going on here. Like, you could have an edge here to come back, but then there's just another edge that comes back to this node, right? If you do it that way. And so you'll get that first cycle where you go back and you do this. And then, yeah, I think it's only really a problem if you don't have an edge that goes out from this node, right? Like if you use this node up too early, quote unquote, use it too early. I mean, is that even possible? I think it only happens, I want to say this only happens if we're exactly one edge into this node. I want to say that that's the case. I don't know if that's the case, though. I don't actually know if that's the case. Excuse me. But yeah, we can actually write this case right now. That'll break this, right? What do we say? This is 3 so 3 will be JFK. It's going to be 2 is better than J. A, B, C, D, E, F, G, H, I, J. H, I, we do I, F, K. And then we have, so this IFK becomes A, B, C, D, F, G, H, I. H, HFK, let's say. A, B, C, D, E, F, G, H. A, B, C, D, E, F, G, H, I, J. A, B, C, D, E, F, G, GFK. GFK, JFK. A, B, C, D, okay, so we want 0, so A, B, C, D, E, F, G, H, I, J, right? G, H, I, J, yeah, okay, so that's what we want. So G is 0, that's when we want to end at G, and we have A, B, C, D, E, F, G, H is, yeah, it's going to go here. I is 2, and J is 3. Okay, J, I, okay, that's what we want, yeah. So we want 3 to 2, 2 to 1, 1 to 0, 3 to 2, 2 to 1, 1 to 0, which we have. And now we want 1 to 3, which is what? J, I, H, G. J-I-H-G. J is 3, I is 2, H is 1, G is 0. I'm sorry, my brain is freaking melting right now. Oh boy. We want 1 to 3. 3 is J, 1 is H. So H back to JFK. I know this is going to be so difficult to add this extra. And now, okay, yeah, so if we throw in this test case, so there's really, yeah, there's 1, 2, 3, and there's this extra 1. Oh yeah, 3 to 1 and 1 to 3, right? Back and forth, these two tickets. With both directions here. So we should run into a problem with this one. Wrong answer on the third one. Yeah. And the reason, and you notice we end up cutting off. We don't visit all the edges, right? It's not right. Now the problem is if we add these two edges, this another 1 to 0 and another 0 to 3, right? Go 1 to 0 and 0 to 3 again. 1 to 0 and 0 to 3. 1 to 0 and 0 to 3. 1 to 0 and 0 to 3. 1 to 0 and 0 to 3 would be. Sorry, I'm just thinking memories, man. I've got all these freaking memories that I don't want. I've got all these memories of things that I don't want to think about, I want to know about. They just kind of pop in from time to time. It's horrible. It's a nightmare. I don't know what to do about it. I know what I could do, but it won't work, right? I can't do it. I can't do those things. Just like tortured and tormented. I really wish, man, I wish I knew, I don't know how to say it. Like I wish, it's a weird thing to say, but it's like I wish I knew God sooner. And I wish I knew my parents knew God sooner. Because there's so much pain that I wouldn't experience. So many painful things I would have just been totally spared from. I mean, I went so many years of my life like that. It's like, that's horrible. You're just gonna suffer horrifically. I mean, I made it out okay, sort of, but not exactly, not really. No, things. Oh man. Yeah, it's like, that hurts a lot. That hurts a lot. Those things hurt a lot. Those things are painful. Yeah, that's upsetting. That's really upsetting. Sorry, I'm just like, yeah, a lot of anger, you know, a lot of anger, a lot of resentment, a lot of bitterness. It's not right, you know. You gotta trust God. You know, God loves you. He's got something for you. It's way better. It's way better. Way, way, way better. Whatever it was, whatever it is, He's got something for you that's so much better. Do not need to be bitter, resentful, or complain. You know, it's not. You know, the thing too about like rejection and torment and all of that, it's like those things are good because the thing that whatever it wasn't going to work out. You know, there was no way it was going to work. And yeah, and I'm free, man. I'm free. Like I'm free from the burden of whatever that was, whatever that might have been, whatever that could have been, whatever that it would have been horrible. Would have been a horrendous nightmare. and it not only would it have been a nightmare, but I'm free from it. I'm free. It's trust God, trust God. It was the right thing to do, and it was painful, and maybe I didn't need to increase the pain. That probably wasn't the right thing to do. Didn't need that. However, the choices that I made were correct. I mean, they were right. Some of them, right, obviously. Some of them. Yeah, man, the pain of loss, the pain of like missed, lowered expectations, loss, failure. God, just trust what God has for you, right? Trust what God has for you. Don't get yourself into a mess because you think you can do better than God, right? Gotta trust Him. Got to trust Him. Something to think about. Anyway, so yeah, man, I could cry. Could cry at some of these things. But it's not. I'm very lucky, overall. I'm extremely lucky. It's way more than I deserve. Just, Just want to take a moment. Just kind of sit and think for a moment here. Did I add these tickets? I did, right? It's got to be a ticket from 0 to 3 and from 1 to 0. So 1 to 0 would be what do we say 0 was? It is 0 is GFK, and 1 to 0 is HFK, GFK. Yes, we put that twice. And then we want 0 to 3, which is JFK. Right, now the question is, so this should still give us the wrong answer. But my question is, do we get the right answer on this, on the one at the bottom? Or do we still get cut off? I wanted to test that. And it looks like it's still wrong. Yeah, see, that's what I'm a little bit concerned about. I was hoping that I could come up with an algorithm that would fix that, so to speak. But no, that doesn't work. Doesn't do it. No, it doesn't fix this. Because what did we end up picking, right? We ended up doing, if we go orange, let's say, and we say two. No, actually, we would go to 1 first, right? We want better than 2. We want to go to 1 first. Then we want to go to 0. Then we can only go to 3. 1, 0, oops, 1, okay, 1, 0, can only go to 3 from there, 1, 0, 3, can't go back to 1, 2, 1, 0, 2, only option we have there is 1, and then back to 0. No, this should be correct, yeah? What happened? Why would this not give me the right answer? Am I crazy? Yeah, it's a lot of pain, man. Just the thoughts that I have. It's a lot of pain. It's pretty unfortunate. But what are you gonna do, man? It is what it is. It's reality. It's just reality. Why? I think this is wrong for a different reason. For a reason I don't realize. Yeah, man, way too much pain. Way too much pain. I did the right thing, though. I did the right thing. It's just hard. It's just hard. It's just hard. That's all. So, yeah, I hate that. I hate that. Like, I know, I know what I can do to alleviate that, to remove that. I know it can be done, but it's so hard. It's too hard. It's too much. It's way too hard. Man, I don't know what's wrong. Ah, it's depressing. Actually, that's downright depressing. that's so painful. Sorry, I realize I'm not really giving you anything to work with to understand what I'm talking about, but just you could probably imagine. You could probably guess. I don't think I really need to give you too much detail. You can probably figure it out for yourself. There are certain things in life that are extremely painful, and that's that, I guess. So at the end here, how do we get stuck? How does that happen, right? I kind of do want to just change these to numbers altogether. We could do that. That might make things a little bit easier. So we said 3 for JFK, 2 for IFK, 1 for HFK, and 0 for GFK. So HFK I think was, so we have 3 to 2, 2 to 1, 1 to 0, and then 3 to 1, and 1 to 3, and then we also have 0 back to 3, and 1 to 0. 0, we have 3 to 2, 2 to 1, 1 to 0, 3 to 1, 1 to 3, and then 0 to 3, and 1 to 0. Yeah, 0 to 3 and 1 to 0. Yeah, and so this, what does this do? What do we get here if we do this? This should be sort of equivalent, right? Same number of tickets. I think I may have gotten confused here. 1, 2, 3, 4, 5, 6, 7, 7. 1, 2, 3, 4, 5, 6, 7. Okay, let's see that. All right, what happens here? Oh, whoops. Okay. JFK is 3. That's awkward. Oh no. Oh, that's exactly why. Okay. Well, actually, that's fine, right? J is larger than all of these things. JFK. Yeah, I think so. I think it still works. I hope it still works. I hope it still works. It's confusing, but hopefully it still works. Wrong answer. Expected. Oh, what's this 3? Wait. That's gotta be JFK. That's my mistake. Shoot. Forgot I have something over there. Smacked my glasses right into a metal chair. Didn't break them, but it's not good, you know. Don't damage your glasses if you can. So JFK 1 0, JFK 2 1 0. So what happened here? Oops. Yeah, thank God, man. I don't know. Just to think about, my decisions. Like that's, thank God, thank God. Just thank God things didn't go the way that I would. Things didn't go the way that I would have wanted them to, right? Like thank God. I mean, things are going the way that I want them to. It's just, like I said, it's just thank God. Thank God they're going the way that exactly as they should. I did the right things. The first things that I had done were wrong, really. Get myself into a particular mess situation. That was the thing that I did that was wrong. In the first place. So I wasn't following God, I was following my own selfishness. Well, actually, I wouldn't say that. At that point, that was kind of not totally wrong. It was wrong. I take it back. No, it was. I was definitely following my own selfishness, my own desires. Right? Had nothing to do with God. Certainly not. No. No. No, I can't even pretend for a moment. All right, so we would want to go to, we would go to 1 first. Yeah, that's fine. 1, 0. Only one way out of here. Only one way out of here. Oh. Yeah. And then we're done. Dead in the water here. And to get 3. That's why. Okay, that makes sense. Well, actually, we ended up down at the 0. What? Oh, yeah. Right. Excuse me. I'm sorry. That's wrong. This is better. This is better. Only way to go. Only where to go. Only where to go. And then we die here. That's what happened, and that's why we missed the JFK there. So what's the solution? Like, what's the answer? How do we fix this? Well, I don't know. I guess it's not the right answer. I guess it's just not the correct approach. You know what? So basically you have cycles, right? You have a bunch of cycles, and they're connected to each other. So you have this cycle, you have another cycle, and then you've got one extra edge, sort of. Like, I want to say something to the effect of, have all these different disjoint cycles in your graph, and you pretty much want to order like how you enter and exit these cycles, sort of. No, that doesn't really make sense. It doesn't really work either. I don't know, man. This is kind of this is an interesting question. I don't know. I'm struggling with it. Oops, what did we? What do we just do? I didn't mean to add these things. I don't know what those are. Gotta think about this for a while here, for a bit. Excuse me. It's a tricky thing, isn't it? So one idea I had was to connect the last ticket from the destination back to the starting point and go through the whole algorithm, get all the cycles and whatnot, get the whole not just mapping, but the whole get the whole cycle, the order of it, and then get the whole cycle, the ordering of the whole cycle, and then remove the edge, right? Remove that last jump. But the problem with that is that you end up with with what I just had, right? You'll end up with the same answer. Like what I just had, it would just stop right there, right? You get stuck. So basically, what tends to happen is you prioritize in such a way that you get stuck. That you don't use one of the cycles that you're supposed to use. That's really what it comes down to. You end up not using one of the cycles that you're supposed to use before you end up in the end point. You can actually end up doing that. Which is so weird, right? We did do that, right? We said we just went and did. How did it work? It's a good thing we tested this. How did we do that? We went 3 to 1. Let me do it again. 3 to 1 to 0, 3 to 1 to 0 to the only place we can go, to 2, the only place we can go, to 1, and then back to 0. Yeah, and somehow we missed an edge. Somehow we missed an edge. What's the correct answer? I don't even know. I guess it would be probably 1, probably 0. Only way out is back to 3. Then, no, you can't do that, right? That won't work. That's actually what the algorithm that I wrote does. We'd want to go 1 instead of 2, definitely, and then back, I think. Take care of that cycle. And then go 2, only way out here. Oh no, these are all, this is all, wait, yeah, it's fine. Yeah, okay, I think we're okay. So 1, back, 2, 1. No, man, we can't. Can we even have a, is this, no. 1, no, this doesn't work. Oh, this doesn't even have a path. Am I nuts? This doesn't even have a path from JFK. Oh, come on, man. Need one more edge here. I guess we could make another one to 2. You need to have 1, 2, 3 outbound and 2 inbound, and then this has 2 outbound and 1 inbound. No. This has to have, okay, all right, let's just make this one go back. Let's do that. So this has 1, 2 inbound and 3 outbound, and this has 3 inbound and 1 outbound. One more outbound. And this has got to have another outbound. Oh man. Why is this so hard? Why is this so difficult? Two out, 1 in, 1 in. This has to have more in than out. So you can have 1 out, and then you can have 1 more in. But now this has too many out, so it needs to have another 1 in. So we go from 2 again. And then in has too many, so you need to have 1 more in here. So you have 1, 2, 3 out, 2 in, and this is 2 in, 1 out. Right, there you go. Oh boy, look at this. Look at this, man. 1, 2, all right, let's get rid of this. Let's say, how many tickets do we have? 1, 2, 3, 4, 5, 6, 7. Oh boy, I can't even count all these. 1, 2, let me just do it this way. 1, 2, 3, 4, 5, 6, 7. 8, 9. Is that everybody? I think so. 9 of them? Okay, 9 edges here. All right, we'll do JFK to 2 twice. This is gonna be interesting. JFK to 1 and then 1 to JFK. Then we're going to have 2 to 1 twice. And then we're going to have 0 to JFK, and these ones, and 1 to 0 twice. 0 to JFK and 1 to 0 twice. Whoops, no! Oh no! I didn't mean to submit it. I don't think we did. I think we're okay. So what do you say? 1 to 0 twice. Nine. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there's one more. 1 to 0 twice, and then 0 to JFK once. Okay. What happens here? Wrong answer. All right, still wrong. Shucks. Shucks. 3 in, 3 out. 2 out, 1 in. Or no, 2 in, 1 out. 2 in, 2 out. And this is 3 out and 2 in. Okay. So we still get the wrong answer though. I mean, it still is wrong. So go to 1. We go to 0. Only one way out. Only one way out. Only one way out. We would still go back to 0 and still be in the wrong spot. Yeah. Okay, that was kind of my point, was that we would still get the wrong answer even if we like modified the picture. And now you could get away from that one node. Like, it's not enough to just kind of remove nodes. So like, we know this has to come last, this one. However, we don't necessarily know which inbound node is going to be the one that we take to get there, right? That's kind of the problem. It's kind of the issue. Same thing here, like we don't actually know which outbound node should be the first one that we take from here. So that's the question that we have. We don't actually know which one's the best. Because basically it's a greedy algorithm, right? That's what we were trying to do. If we tried to use a greedy algorithm, it just wouldn't be correct, right? Our greedy algorithm just wouldn't be correct. It wouldn't be right. If we use a greedy algorithm or try to use a greedy algorithm, it would not work. Oh man, I'm sorry. I'm so sad. I'm just so sad, man. I can't. I don't know. I don't know what's wrong with me. Just sad. Just sad. Like, that's all I could say. I could think of. Shouldn't be this sad though. There's no reason for it. There's no need for it. It's have the joy of Christ or joy of God, right? Like follow God. You know, I don't know. I don't know. I don't know. Yeah, ouch. Ouch, 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 ouch. Just be at peace with what God has for you. Yeah, that's hard. That's hard. That is hard. That's really hard. Sorry. So, okay. So JFK 210. We want. Well, I don't have a solution. I don't have a solution. I don't. If we connect these two nodes right at the back, right, the 0 and the JFK, put another connection, we run into the same problem. Even though a greedy algorithm would give us a circuit, however, we wouldn't be able to follow that circuit if we deleted that node, that edge. It would be the wrong. It would just, that what we got would be wrong. What I just described would be wrong. So can't use that approach. Cannot do it. Won't work. Okay, let's try something different. Some other idea, different approach. What about? Sorry, I'm just thinking about things, man. Oh man. Oh man. Just so sad. I'm just so sad. Yeah, sorry. I'm sorry. I'm sorry. So ouch. Ouch, 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 ouch. Some really painful things. Just some really painful things, that's all. Keep coming to my mind. When I get stuck, it's like I just start thinking about other things. So now my question is, should I look at Helmholtzer's algorithm? I guess that's I'm wondering if I should do that. I don't think. This is a tricky thing, man, because not only are we looking for it's kind of complicated, right? Because we're looking for, if you look through all the possible paths, trails, there really aren't that many, are there? It seems like there's a lot. However, really there's only No, actually, there could be a lot. There could be quite a few. The reason there could be quite a few is that you're looking for you want to set these cycles up correctly. You're cycling through different nodes. You have a bunch of disjoint cycles. And then finally, once you've used all of those, you have sort of an ending node. That's not part of a cycle. An edge, I guess it's not part of a cycle. I want to say something like you could maybe perform your greedy algorithm removing each one of these inbound edges, right? Basically selecting an inbound edge. And if you were to do that, well, you run into some problems, don't you? Yeah, because you gotta get rid of one of these outbound edges too. Then you kind of have to fix the whole graph to do it that way. That doesn't really work. It doesn't really work. No, I don't know. Let me lay down for a few minutes and think about it. I don't really have the answer. I don't really have the answer here. Oh. So. Excuse me. Oh, man. Helmholtzer's algorithm, huh? I could probably look into it. And I guess that would give me all of the different paths. It's just... and I guess I could take the best. See, that's the thing, is I don't know that it's... I don't know if you're just detecting that there is a cycle. See, there really is... Just gotta think here. Maybe we can do it this way. Maybe we could do like a breadth first search. I would say, okay, what we're gonna do is we're gonna take all of the edges to consider. We're gonna pick one, and we're gonna say, if the node that we're going to has an outbound edge, has at least two outbound edges. See, I guess that's the problem, is that you could end up in a situation where if you take the greedy approach, you might just get stuck. Well, I mean, maybe we can just do a single. I want to say that the look ahead has to be kind of advanced. Like, it's not enough to just have a single look ahead. I want to say something like it. With just a look ahead, we can make sure that we don't pick the wrong option, right? Like, we can kind of take whatever path we want through the graph, but there's a certain point where we get into trouble. So specifically, that's when. So let's try our greedy algorithm again. Right? 2, 1, 0. No, I'm sorry. It goes 1, 0 only way out. 2, only way out. Now we don't pick 0 because there's only one way to 0. Like we've used all of the edges to get to 0. So we go back to JFK, back to 2, back to 1, back to 0. I think that actually works. I think because this has to have somewhere else to go, right? If it only has, if you only have one outbound edge, yeah, something like that. I want to say that you just don't choose the node that it's kind of a problem there though. If you only have one outbound edge or no outbound edges, that pretty much should that should be the only time you select of your choice of nodes, the only time you select the node that has one outbound edge is if that's your only option. Yeah. Let's do it that way. Yeah, so let's do it that way. Okay, that's an idea. So always pick the nodes that have at least one more outgoing edge, unless it's the only option you have. Let's modify our algorithm that way. It would work on this test case. I wonder if it'll work on other test cases too. I'll make that small modification. Hopefully that makes sense. Hopefully that makes sense. Let me go ahead and I kind of want to like just take a break and go to sleep. Like I'm like ready for bed, man. I'm so tired. Also, like I said, I'm like really upset too. I don't know why I've been so upset lately. You know what it is? I've been learning and reading and hearing about a lot of really sad things. I think. Like I've been learning about, like there were all these, there's all this stuff, man. There's so much. I have my own problems that I gotta deal with, like things that are really just difficult, and then I have things like I would want to make YouTube videos about stuff, but I kind of don't want to do those things. Like a part of me feels like I should be more focused on like what's in front of me. And then another part of me is like, yeah, I would like to do those things. But they're also like really sad things, and I don't even know how to present them or express them. You know, I'm kind of like pretty conflicted about how to even package this stuff up to kind of give it to the world. And a lot of it has to do with like rape and like children and, you know, just incest and like really horrible things. Like it's like really terrible stuff. The reason I wanted to talk about it is that like, well, there's sort of a lot of good that can be done by just avoiding harm, and there's a lot of harm that can be prevented, and it's like basically talking about how to avoid a lot of these things, and not just avoid these things, but even when these things happen, how to avoid making things even worse, like, you know, 1,000 times worse. And like, I would like to talk about those things. However, I don't want to do anything at the same time. Like I just want to like lay down and stare at the ceiling for, you know, the next 800 hours, something like that. Yeah, I just, man. Anyway, just I have my own problems, you know. I just have my extremely painful memories, tremendous amount of resentment. Like the resentment is just like, it's killing me, man. Like I don't know how to stop being so resentful. And then yeah, I'm just frustrated too. Like I got all these things, Anyway, a lot of unsuccessful things. Let's say, put it that way. A lot of very unsuccessful things. But doesn't, it's not gonna be like that forever. Like it doesn't need to be like that. It's not gonna be like that forever. It's just, I don't know. I guess just it is what it is. I gotta just thank God for my life. Just be grateful. Be grateful. Be alive. Like thank God. Thank God. All right. So this is what we're going to do. We want to implement this extra rule where we say we're not going to pick a node if that node has only one outgoing edge, or no, it has to have a greater than or equal to 2 outbound edges. Yeah, so, okay. Select an edge according to the following rule. If the edge has less than 2 outbound edges, select it only when there is no other choice. So we'd say if g of which dot size or dot, yeah, I think it's size, well, yeah. So we'll do this. Oops. So say iterator, okay, is equal to which begin. Well, I want to say something like while, so let's say, oops. Say int outbound edges equals g dot count of this iterator, right? While outbound edges, so we say if g dot count of which is equal to 1, is not equal to 1, it's greater than 1, then only when there's no other choice. If there are, yeah, there should only be one. That should only happen once. Yeah, we shouldn't. I was gonna say if there are multiple choices where the nodes only have one outbound edge, that is actually, that is possible. Could be more than one. Okay, then we pick the one with the lexicographically smallest. All of the edges have only one bound edge. So, I don't know, how do we handle this? There's like a few ways to do this, that we could do this. So let's see. So let's do if, So yeah, start with this. If g.count of which is greater than 1, then we're gonna look to update. So if it's equal to 1, then that's it. We just take that. Check are any nodes, neighbors, with an outbound edge, out degree, I'll call it out degree. Let's check if there are any neighbors with an out degree greater than 1. So we can do auto temp equals g of which begin while g of temp dot count is g count dot temp is less than or equal to 1. We're going to advance temp by 1. Right? We say if temp is not equal to g of which dot end, so if we haven't gone all the way off the edge, then any neighbors that not degree greater than 1. If it's not equal to the end, then we set iterator equal to temp. Otherwise, iterator stays the same. Right? Yeah, there you go. This is kind of a rule. Something like this. Let's see what happens if we do this. Does that compile? Yeah, it compiles, but it's still wrong. It's kind of interesting. Huh, really? This is still wrong? I wasn't expecting that. Pretty sure it's correct, right? So we go to 1, we go to 0, we go back, we go to 2, we go to 1, and now we have a choice between, hold on. We actually remove these. Yeah, we remove these. Right, we said go to 1, go to 0, go to JFK, 2. Now, the number of outbound edges for 0 is really low. Right, we wouldn't pick 0. We would pick, never mind. I have to pick the, oh no. That's awkward. There's one more detail here. Do not select the node with no outbound edges until the only option left. Similarly, choose any node with one edge over any node with one edge over a node with no edges. That's what we're doing wrong here. Okay, just a slight modification. Come on, really? You gotta be kidding me. No! What? What do you mean? What? No. Come on, really? Really? What? What? No. No. Okay. 2, 1, and this should be JFK instead of 0. Really did 2. So how does that work? We go. You're telling me that you're going like so. JFK to 1. So then you go to 0. Back to JFK, it's the only place you can go. Back to 2, it's the only place to go. Back to 1. And you're going to 0 instead of JFK. No. You should be going to JFK now. Why? This should be correct. Alright, but somehow my logic is just wrong. I mean, I have this idea that, I'm not even sure if the idea is right. I'll probably be wrong in some test cases, but in this case, it's not coming out right. So here we say count is greater than 1, which it is, right? And we're looking at this 0. We're at 1, really. Are there any neighbors with an out degree greater than 1? Time to begin. Well, they're less than or equal to 1, which they are. Both of them are. So this should advance twice. Straight off the bat, out the edge. Straight off a cliff here. And temp's not equal to g of which end? It equals temp. Right, so you find something that's, yeah, but otherwise, if we don't go to the edge, no, this should go right to the end. Yeah, it goes right to the end. So if it goes right to the end, we want to take a look at if what you're looking at is the 0, it's this one, There should be 0 outbound edges. And then we want to advance this to... So first things first, does this even get called? No. Alright, something funky's going on here, something I don't understand is happening. Check 1, check 2. This should get called a bunch of times. What? What? I'm very confused. What is going on, man? Okay, yes, so check 3 gets called a few times. G count of which? Oh, this really is just to see if this is in the... Oh, my eye is killing me, man. I'm sorry, I think I understand now. Okay. G count just checks if the key is in the map. That's really it. Whoops. Whoopsies. Runtime error, nice. It's always good. Also, it sounds like people are like partying or something. I don't know what I'm hearing. Oh, I need to. Do I want to keep charging this? So yeah, so I'll start lowering my voice though. It's about time to kind of start lowering my voice. Because people are gonna start going to bed. So it's like 8 p.m. All right, so there's a runtime error here. Oh boy. Okay. What happened? Where's that runtime error happening? Check 1, check 1, check 1, and then no, it doesn't happen there. Oh. I think I see the problem. No, 2, check 1, error 2. Check 1. Oh, that was the problem, okay. Right, if it's, yeah, if you dereference before you check that it's, yeah, okay, makes sense. Well, it was still the wrong answer though. What do you mean it's the wrong answer? Oh. Oh, look at that. That's wrong though. Now why is that happening? Can get rid of these debug errors. Well, that shouldn't be a problem. I realize the logic's kind of funky for this, so yeah, this 0 JFK. What JFK 1 0. What? Why would? Okay, let's see. JFK 1 back to JFK. No, it should go back to, it should go to 0. JFK 0, right? There's two options, and this first one has 1 outbound, 2 outbound. Oh, this one has 1 outbound edge. Oh no. Oh. So yeah, my logic doesn't make sense, does it? I don't even know what to say. Really, It's hard because I want to say something like, well, don't choose this vertex here. We can identify this vertex. Don't choose it if, I guess you're on your last limb, right? It's the last, if you choose it, it'll terminate early. Basically, it doesn't have any more outbound edges. That's great, but what if you have like nodes in between, right? What if you have like a couple nodes in between? And you're not choosing, and these have like a few paths, I guess. And you have a few nodes in between, and they have these paths, and what you're looking for is, when you choose one, it's you're choosing one of these. You're not choosing this, which is what I was trying to alleviate with there only being one outbound. That you would prefer the other choices. No, it doesn't work either. Oh no. Uh-oh. Uh-oh. Excuse me. So tempted to just go look at the Helmholtzer algorithm and use that. What do we do here? Oh man. Ugh. I'm gonna lay down again. Think about this some more. Yeah, I don't have a good solution to this. Don't have a simple, obvious one. No, definitely not. Oh. Yeah, I'm really tempted to go look up that algorithm. Excuse me. So. I gotta think about this some more. Oh boy. Yeah, huh. Get this feeling there isn't really a simple, easy answer to this one. You really gotta think about it. Gotta dig deeper. Man. Let's think about this some more. Let's ponder it. Ponder it some more. Let's think about this a little bit more. Yeah, I'm falling asleep over here. Oh man. Okay. So how do we solve this? Excuse me. So yeah, it seems the greedy algorithm breaks down or tends to break down. Oh, that's very loud. I'm sorry for that. Man, I still don't have a solution. You know, I'm still like just thinking about it. I don't know. I mean, I'm really distracted too, but it feels like I might not have a choice other than to basically copy one of these algorithms. I don't know if I just really spend this much time on it thinking about it, because it's just I don't know. It's kind of out of the realm of what I normally think about. I don't know. I mean, I also don't really spend too much time like inventing algorithms. I mean, these exercises for the most part are kind of supposed to be like a mixture of figuring out what I'm supposed to know in the first place and kind of implementing things that I already know. They're not really supposed to be too much of like me creating my own algorithms, if that makes sense. Hopefully that makes sense. I don't know. Maybe I'm just making excuses. Yeah, kind of. I mean, you really gotta like sit and think about a problem if you want to go for the solution. Usually you realize something, you know. Um, um, what was I saying? So, sorry, man. My mind is like just wandering all over the place. Uh, How do we solve this question? This is pegged as a medium question. I guess it's easier if you understand graph theory. I don't know why is it medium? I don't know. I'm not gonna question it. So wondering if there's like a depth first search or breadth first search algorithm we can do. Maybe just breadth first search. So, I mean, technically you could do, maybe you can do like a memoized version of this, something like that. I don't know. I want to say something like, you could do like a recursive approach where you would say, okay, take the smallest of all, of all the possible edges that I could take from this particular node. If from each of those nodes, if an Eulerian path can be completed, then take the smallest node from which it could be completed from there. You could do something like that, but the problem with that is, I don't know. But I guess it's like a backtracking problem, backtracking question, approach. I mean, you really only change like one cycle. Like, you only change a few positions from the greedy approach, the greedy algorithm. Like, you really don't change very much. Yeah, you really only change, it really should only be one decision. Instead of going in too early, you go in a little bit later to that node at the end. Excuse me, but everything else pretty much stays the same. So yeah, it's pretty much greedy the whole way, I guess. It just doesn't seem, I don't know, it just seems very like, Maybe that's what I'm doing wrong. Maybe I should be doing that depth first search algorithm. But use it on a multi-set and be greedy. Use a greedy approach. Greedy depth first search. Maybe that's why this is a medium. Maybe a greedy depth first search is all you need. And it's pretty easy after that. It's pretty easy to do. Let me try that. Let me see what happens. I'm curious now. Yeah, because I think you only really need to change like a couple decisions, you know, and they really the first path you get, if you're using a mostly greedy approach, I think it works. Excuse me. I don't think you need to use Helmholtzer. I think it's called Helmholtzer. Excuse me. So let's see. What did I call it? Or what was it called? Helmholtzer, not Helmholtzer. Helmholtzer. Okay. So let's go back to our. Let's say this. Oh no. Oh yeah. Okay. Let's try this now. Let's do another one of these. Say that this one is wrong. Say that this one is wrong. So this one is correct. However, what I want to do okay, let's try something like this. Ah, look at that. Oh, okay. Still wrong. Oh, really? Oh. Wait a second. Which ones are wrong? These two? 1, 2, 3, 1, 2, 3, 4. These ones are wrong. Let's remove those for a moment. So I'm going to add this to my list of test cases here. So these ones are correct. And but these are wrong. Which ones? These two. These were incorrect. Empty. Really? Oh, I see. Well. Could say. Now this one's interesting. The top one doesn't work correctly. This week we don't need to worry about. But this one, I'm surprised this doesn't work. This is supposed to be a brute force approach. This should work here in theory. Really, it's wrong, huh? Now, is this just this test case? Does this even have a? Does this even make sense? You just abbreviate with J, I, and H, and G. Okay, so J to I to F, I to H, H to G, H to J to J, J to H, H to J, J to H, H to G, and G to J. Yes, this is wrong, right? Oh no, it should be fine, right? This is 2 inbound and 1 outbound. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, what would we expect? We would go J to I don't know. J to H to G to J to I, back here, back to J, G to J. Am I crazy? Am I going nuts here? Why wouldn't this work? Why would we not? Ah, man. Come on. This should work. Don't be afraid, I don't mean to scare you. Ha. 1, 2, 3, 4, 5, 6, 7, 8. I don't know, man. What's wrong? What is wrong? Could just print everything, I guess. Okay. So this is what we did. All right. JFK to H to G to J to I to H back to G again? What? No. J to H to G to J to I to H to G again. Wrong. Oh, there are two H to Gs. How did I do that? Wait, what? JFK, IFK. Am I crazy? Am I nuts? Did I transcribe this incorrectly? Okay. J to I to H, H to G, H to J, H to G, H to J, J to H, H to G again. So that's two of these. And then G to J. Oh, that's probably why. Okay. Yeah, this is incorrect. So this should be G to J, which is I think it's supposed to be J to G here. Yeah. Not H to G. Something like this. Oh, come on, man. It's driving me crazy. annoying. I'm getting these wrong answers because they don't actually have, like, they don't actually have Eulerian cycles. I mean, the algorithm they gave gives a different answer, but basically those are invalid test cases. That's what I want to say. JFK to IFK, IFK to HFK, HFK to GFK. Then we have HFK to JFK, and then JFK to HFK, and then JFK to GFK, and then GFK to JFK. This is correct. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, alright, so now this one should be fine. Now how does this end up being wrong? That's the question. So JFK to GFK. Wait, what? GFK to JFK to HFK to GFK again to JFK again. Oh, that's not correct, right? That's not possible. Oh, my head. What? What is going on? This doesn't make any sense. Oh, man. What is happening? So, yeah. So, okay, so each stop will tell us what the neighbors are. Excuse me. GFK, we get the JFK, JFK. Yeah, we already went to GFK, so we have HFK and IFK. Then we go to HFK, and we have GFK, JFK. Let's go to GFK. And then we're done there. Okay, I see. Got it. And there's no neighbors after that. So that's a dead branch. And JFK, IFK, IFK, HFK. Okay, and I think okay. So confused. Why does this stop come twice? where did this happen? Why did this happen? 1, 2, 3, 4, 5, 6, 7. JFK 3 times. Is that even possible? 1, 2, 3. Yeah, there are. Yeah, it starts there. Comes back once and twice. Yeah, I should see it 3 times. What are they expecting? What's the 1, 2, 3? Yeah. Okay. We never actually get to 8. We never get, like, I'm so confused, man. Why is this not correct? That's what I'm wondering. I thought I had, I just put this after every stop. So neighbors, stop at JFK, GFK, okay. So go JFK, GFK, JFK, JFK, GFK, and then we get stuck. Let's go to JFK, current. Let's back up. Use JFK instead. IFK. Okay, we have 8 here. Okay, this is the answer. This is it. Why did we... What's N? N is 1, 2, 3, 4, 5, 6, 7. Is that because I did this? No. Oh, I'm sorry. That's my mistake. There we go. Okay, I was like, what is going on here? Duh. I was freaking out, man. I'm like trying to figure this out. Like, how is it possible? Alright. Like, this is a brute force solution. Like, it should be correct. It's like, how is this happening? Okay. Alright, so these should all be correct. Wrong. Oh, please no. Didn't we just do this? Oh, right, I didn't fix... This test case that shouldn't work, I think. Yeah, this one doesn't make sense. Oh, shoot. Let me copy this one instead. Yeah, it's an invalid test case. Oh, boy. You gotta be kidding me. It's still the wrong, oh no. What? Dude. Come on. Give me a break. Okay. I got rid of the wrong one, I think. So this one was supposed to replace. I think. Alright, let's try again. I'm gonna be sad if this doesn't work. Okay. Oh, finally. Alright. Now the question is, can we terminate early? So the first time that it even works should be just the only time that you need to. That just be it. So which one is wrong? Really? Two instead of one. Really? That doesn't seem right. It seems like the greedy solution should be the one we use first. What? Why? No. Serious? Let's do the second one, right? Just focus on the second one. So I'm so confused, right? Because, oh, that's why. I'm sorry. I didn't finish the program. Yeah, there we go. It should be the first one that works. Should be correct. It's like I'm at a loss here. I'm at a loss here. Why is it not working? There we go. There you go. That's what I'm saying. Yeah, without this, then the last one is the one you end up using, right? And now, here's the moment of truth. If we do the really long one, throw that in there at the end. See if that still works. Hey, look at that. All right, let's see if we get the right answer. Let's go for it. Hey! genius. Oh, I'm so smart. I mean, I feel like a dummy. I feel like a complete goon after that. That was brutal. That was brutal. At least I did it myself. I did it myself. I figured it out. I do feel a little silly though. Dude. Wow, I feel like I just wasted like so many hours. It's too funny. Yeah. Oh man, that's amazing. That's something else. Yeah, what do you make of that? What do you think of that? What do you do? I don't know, man. That's too funny. That's too funny. I don't even know. I don't even know. Wow. I'm just thinking, how would you do a breadth first search like this? No, I think depth first search is the way to go. And the first time it works, that's it. Terminate early and you're done. That should also be the optimal. Wow. I don't know, man. I used a lot of memory. I mean, maybe there is a way to use less memory to do this. I wouldn't know exactly how. And you could maybe do it faster too. Well, I guess the Helmholtzer algorithm could be used, probably. I'm wondering if we should look at the discussion, probably. But yeah, a greedy terminate early depth first search seems to do the trick. I guess this would be a medium, yeah. Wow, dude. That's amazing. I mean, we did it. We did it. We did it. Ah, we did it. But that's, oh man. That's a hard one. Tricky one. Definitely a tricky one. I struggled with that one for sure. I mean, really simple solution, ultimately. Like this could be done very quickly. I could have done this probably in 5 minutes if I knew sort of what to do. If I had a better sense of things. Yeah, 5 minutes. Let's see if we run it a few times, how many we do better. No. We're slow, man. Everyone else is faster. I'm fairly certain that we're still linear time because you really only need to backtrack once. But it is a lot of memory. So yeah, I bet you Helmholtzer is what everyone else used because you don't need to use nearly as much memory. Wow, I feel so smart. Hey, we did it. Hey. Yeah, I do have to admit though, I do still have all of the same problems and issues that I had before. Still problems and issues that I have. But we're just one LeetCode problem smarter, I guess, or accomplished. I don't know. That's a good feeling though. That's a good feeling when you figure something out and you're like really struggling with it and you're really just not getting it. And you're like, I don't know, man, like you're ready to quit. You're ready to, reconsider your life choices. And it's like, figured it out. And it's always like some thing, some little, not little thing, but it makes it so much simpler once you realize it. Well, anyway, that'll be it for me for tonight. I don't know if I want to revisit this problem. I'm like, excuse me, I'm tempted to come back to this, make a part 3, go over the discussion. I mean, I think that going over the discussion, it probably would be kind of short because the answers would be things I probably already considered. So yeah, that would be interesting. I should do that. We should do that. We'll go over the discussion. We'll come back with a part 3 tomorrow, I guess. But yeah, thank you all for watching. I'll talk to you soon. Have a good rest of your night. And yeah, this was an interesting problem, man. This was a tough one. We did it. We got there. So